So we've been talking about nuclear particles, so on. Last time we talked about how to detect them. What y'all think of the lab? Did you like that? Do you like to hear the clicks? Whenever you hear those clicks, it kind of makes you nervous, especially the smoke detector. Yeah. So what that tells us is that our instruments for detecting radiation are really sensitive. So today we're going to learn about what the thresholds are for damage to our bodies. And so there's a detectable sort of no adverse effect level below that. We can detect radiation well below that. And so there's sort of a threshold in our bodies above which we can detect some physiological response. So we'll discuss that today and talk about nuclear medicine too. Whoops, back. Where'd you go? There we go. And so this is all of the environmental insults. I mean, we live in a radioactive world, and so we have 50 millirem per year coming in from cosmic radiation just because we live 8 minutes from a fusion reactor, and the sun is just blasting us with, 5 million exajoules a year. The radioactive elements in our planet, we get irradiated from those. We turn a lot of those iron ores and so on into bricks and put them around our home, and so we're getting 3 millirem per year from bricks and mortar in our houses. Human tissues, so eating argon is if you notice, 40, and so is potassium. So radioactive potassium in the soil and in our food supply and so on will decay and become argon. So there's roughly 1% argon in the atmosphere from the decay of radioactive potassium. So that's one of the more common radioactive elements in our bodies. So we're radiating ourselves by our diet. And so I don't like swear off bananas. No, I'm teasing. Um, then from air, so just radon in the air. Also, there is a chance of having some spontaneous fission, and so spontaneous fission will be the elements breaking apart, not just spitting out an alpha particle or beta particle, but breaking into half, if you will, and producing radioactive krypton, radioactive argon, and so on. So there's some trace amounts of gases that just occur naturally from spontaneous fission in uranium deposits. The uranium decay series produces radon, so the most common source of radiation in the air is from radon. So sum up all these natural sources, we're talking about 126 millirem per year. So that's detectable. Then human sources, so X-ray diagnosis, if you go get a dental X-ray, or if you have an X-ray, if you got something wrong with your ankle, you twist your ankle, you get an X-ray, you're getting some ionizable radiation. So that's not really a nuclear radiation process, but it still is above that ionization threshold. So it's ionizing radiation. Of course, if you have cancer and you get radiotherapy, then you would have a higher dose. The nuclear power industry, because they want to shield the reactor from the environment, has actually got a very low dose. But it does produce, again, some trace krypton and radioactive elements, maybe some radon and so on. And that's dispersed in the atmosphere. So we're getting a small amount of dose just from the existence of the nuclear power industry. TVs and monitors, probably not anything nowadays, but this is dating back to the days when we had cathode ray tubes. And so what is a cathode ray tube? A cathode ray is an electron beam, and it's coming off the cathode, going towards the anode, and the anode is the screen, and they're spraying electrons on the screen, and they excite phosphors that emit light. And so they're writing the image on the screen with an electron gun. And that can knock out some core electrons. If it knocks out a core electron, then you get an X-ray that's emitted. And so the X-rays are coming out of the cathode ray tubes, but it's very low intensity. But still, they knew that was in existence. And so all like my generation, our moms always told us, don't sit so close to the TV, it's radioactive, So technically, yes, but not enough to do any damage, really. So 2 millirem per year, maybe. And then radioactive fallout from our nuclear testing, not just ours, but Russia, France, England, people that did testing in the atmosphere, the the incredible heat from that blast would create a column. So the mushroom cloud is a column of heat, and all that heat rising and blowing those radionuclides up at, you know, golly, 60,000 feet. Our airplanes fly at 30,000 feet, so like twice as high as the airplane, and then that just gets distributed over the globe and diluted. But it's an immeasurable amount. So you could have a nuclear blast, say in the Pacific, and you could fly airplanes with detectors on them, and you could measure the radioactive plume and where it goes around the globe. And they would say things like, this radioactive cloud circles the globe 5 or 6 times. So it's kind of interesting. So total human sources add up to even less than the natural sources, so 67 millirem per year. So that's the grand total. Now, if you live in a high radon environment, you can add like more than double that, well, double it to this dose, because wherever there's radon, wherever there's uranium deposits in the soil, you have a higher intensity of radon gas in that area. So this is the sort of the map of the United States where radon is a risk. So you can see we're not at risk in Texas at all. So the amount of fraction 0 to 0.05 in Texas. So that's why we don't have radon detectors in our basements and so on. So, but my cousins, that when they lived up in Pennsylvania, they were up near Philadelphia, they had a radon detector in their basement. And so it was just a little absorbent disc, I guess, I don't know, but they would have this little vent tube, so the basement was vented out to the atmosphere, and then also they had a little like canister, and I don't know, they were part of some monitoring program. Some agency would come and swap out that canister and then go measure the radon and see if it was being expelled from the basement. Now, why the basement? Well, radon's a heavy gas, so it's going to stratify. It's going to be the lower part of the floor or a basement. Second, it's coming out of the ground. So it's going to go percolate through the rock and through the moisture and also through the concrete in the basement. So it's going to collect in the basement. So if you have a really energy efficient home and you've sealed up this exchange of air with the outside to make it, stay cold inside in the summer and hot inside in the winter, then you're also trapping radon gas if you're in a radon area. So they said that after they did an energy efficient push in the 70s to try to save fuel and so on, it's a sort of an energy crisis in the late 70s. We had lines at the gas. Have y'all heard about the gas lines and all of that? So when I was a kid, we had gasoline lines. You had to go wait in line to get gasoline at the pump. And if your license plate number ended in an odd number, you could go on odd days. And if it was an even number, you could go on even days to try to distribute the lines and stuff like that. It was crazy. And so there was a big push to save energy. So everybody started sealing up their homes with insulating tape and so on, and make sure there were no drafts going through the doors to save energy. Well, then lung cancer started to spike because the radon gas was getting trapped in homes where you see the red and green areas up here. That's primarily where it was. So what's going on with radiation? In your lab, you've dealt with radioactive substances. You had the Fiesta plate, you had the smoke detector. Did you see the green glass? The green glass was uranium glass from like the Depression era glass. Sometimes they call it depression glass. It has uranium in it, and it gives it that green optical color. And if you stick the meter on it, you really don't detect much of an increase in radioactivity, even though uranium is a radioactive element. But uranium-238 has a 4.5 billion year half-life. So it's not producing a lot of particles. But anyway, when this ionization, these alpha particles, beta particles, and so on are produced, if they're outside the body, it's pretty safe. The alpha particles can be stopped by the dead skin cells. So they don't even penetrate into the dermis. Okay? Beta particles can get into the skin and pretty deep into tissue, and then gamma rays will go straight through. Gamma rays are typically absorbed by the heavier elements, and so if you wanted to sort of capture gamma rays, you would need the lead is ideal because it's cheap. It's got a big fat nucleus. It's going to interact with gamma rays. Now you can get some interaction with iron. And what happens with iron nuclei, if I'm correct in this, is they will absorb gamma rays and then transfer them to other gamma rays that will then activate nitrogen. So that can be a problem. Okay, but again, you'd need an enormous gamma ray flux. Now, when it does damage the cells, it affects those cells that are rapidly dividing. And so these are the areas where cells are rapidly dividing. In your bone marrow, where you're making red blood cells, and in your lymph nodes, where you're making your immune response cells. And so these tissues are affected, dramatically with radiation. And so if you had a radioactive release or an event, you would see things like lymphomas and blood cancers. But cancer cells are also rapidly dividing. And so a cancer cell has got something wrong with its programming. There's been some mutation where now it's rapidly dividing, but then that also makes it more susceptible to radiation. So that explains why we can use radiation or have radiation cause cancer in some cases, but then also use it to treat cancer. That always made me wonder, how does that work? How am I using, if radiation can cause cancer, how is it used to treat cancer? Well, it can destroy those cells too. They're susceptible to being affected by radiation. Also, young children, including preborn children, they're growing so fast, they're very susceptible to radiation effects. So this is what we define as ionizing radiation, energy that's above the first ionization energy of water. So that includes UV light and X-rays. Okay. And here's our thresholds. So this is the no detectable clinical effects of below 25 rem. Look here. So this is rem. And our natural sources were around 193 or 200 millirem, so 0.2 rem. So that's what we get per year, 0.2 rem per year. So we can detect this really, really low level. We were calculating like 13 counts per minute background radiation in our lab. So 13 counts per minute, and 1,000 counts per minute is 1 millirem per hour. Yeah. So we're really low background radiation in the lab. So we would need to have, like I said, we would need to eat that little pellet of americium-241 to get it in our bodies, to multiply the alpha emission by 20 and have a detectable health effect of that. Like we might see a temporary decrease in white blood cell counts if we ate that americium tablet. Okay, we would probably not get to the point where we felt nauseous, started running a fever or anything like that. We certainly wouldn't get to the 500 rem level. There's just not enough americium there to deliver that much radioactivity to our body. But that's the LD50. So this is LD50. And that means 50%. So death of half of the exposed population within 30 days of exposure. So 500 rem is the LD50 for radioactivity. I put the sieverts in there too, just for those that want to think in sieverts. Now, employees at nuclear facilities and power plants wear dosimeters. So one of the very first things Röntgen discovered when he discovered radioactivity, he discovered X-rays actually. He had some uranium ore, and they knew this uranium ore was strange. It seemed to emit energy in some form, but they didn't really know how to measure it. They didn't know how to characterize it. And he had some photographic plates in his drawer, and he put the uranium ore on top of the photographic plate and put it in the dark. And then he came back and he developed that photographic plate, and he could see the outline of the rock. Like he could see where the rock had exposed film. And so this was his first discovery of radioactivity. And so then he took the uranium and I guess that, I don't know if he had purified it or not, but anyway, he had a radioactive source now that came from that uranium, and he had a photographic plate, and he put his wife's hand on the photographic plate and put the radioactive powder or whatever it was above that and let it sit for a long time, and then he got an X-ray image of her hand with her wedding ring. And so it was like the first radiograph that was ever made, and it was in the 1800s. And so then Marie Curie extracted the radioactive elements from pitchblende, and she was able to extract elements like polonium, and radium was the one that she was able to concentrate the most, and so she had radium, because you see it's right below barium, and so in all this precipitation scheme, if you separate, say, the hydroxyl precipitates and the sulfur precipitates, and you get to the sulfate precipitates, you're getting group 2. So the group 2 elements from sort of calcium on down will precipitate with sulfate. And so when she precipitates that, she gets a lot of barium, but some of that is also radium. And so she had a pretty radioactive sample. And then they were using that in World War I to image people and find bullets. So they had a fluoroscope, so like a zinc selenide screen that would fluoresce when these ionizing particles hit that screen, and they had the fluoroscope on top and the radium source on bottom, and they would slide a stretcher in the way, like move the person up and down until they found the dark spot where the bullet was, like in a leg or in the body, and it was kind of like a MASH unit, if you ever seen that show. You know, they come up with they had a Jeep, they had the fluoroscope on the back of the Jeep, they'd slide the stretcher in, find the bullet, then take them over to surgery and cut it out. And so that was, I mean, she was amazing. So that's where this dosimetry came from. So a dosimeter is just a piece of film. And so then if you're working in a radioactive environment, that film is going to get exposed. And so they go and they measure the percent exposure, and they calculate what your dose was. So we always had these film badges. Whenever we went down to work with the radioactive material, we had to put on our dosimeter. They would come by each month, pull it off the board, and go develop it, and then we'd get a report how much radiation we got in the last month. So after, let's say, in this case for a nuclear facility here, when your exposure goes over half a rem, that's 500 millirem, in 3 months, you were pulled off your duties. Now, this is the program, or the goal in all nuclear facilities is ALARA. So that's to keep your dose as low as reasonably achievable. So the reasonably achievable part is you still got to do your job, right? Like, let's say at Pantex, your job is to dismantle nuclear weapons because we have treaties that say we will dismantle them to this level or whatever. So we're doing that. And so we still want to do the job, but we want to keep the dose as low as possible. So let's say if I were to dismantle the whole system, my dose would go over this 0.1 millirem per year, or 0.1 rem per year. So can we put 2 people on that job? And so I do it for half a year. Then my dose is cut in half, and the other person has half the dose too. So that's what you would do. And if it makes sense business-wise and production-wise to have 2 people do that job to keep their doses reasonably achievable, as low as reasonably achievable, then that's what companies will do. Pantex is, again, our nuclear weapons assembly and disassembly plant, and that's where I work. So I'm very familiar operating at the 100 millirem per year level. But in nuclear facilities, they let them go up to half a rem, or 500 millirem in 3 months. So that's 1/4 of a year. So they might get 2 rem per year at max. Okay, and that's still 2 versus 25. So they have a factor of 10 in terms of safety. So they're at 1/10 of the threshold level at their max. So this is sort of an analysis of the one, I guess, most recent nuclear meltdown that we've had. This was in Fukushima, Japan. There was a tsunami, and they had a generator here that was on I think it was a 5 meter, which is pretty tall, a 5 meter tower. Okay. And here's their generator. It's a diesel generator. And you think, well, this is a nuclear power plant. Why do you need a generator? Well, if something happens, okay, then you need backup power. And so there was an earthquake, and as soon as the reactor, system detected the earthquake, it shut down the nuclear reactor. But this thing is super hot, right? So they dropped the control rods in, and they started cooling the reactor down. And so that's what's going on with the reactor. But over here on the side, you have this spent fuel pool. Okay. And remember, if we get spontaneous fission, you have to add up the neutrons and the protons to make, let's say uranium breaks apart. Uranium was over here at 92 and 238, and it breaks apart and it produces a crazy isotope of krypton and a crazy isotope of barium that have like way wrong numbers of neutrons. And so then those elements are incredibly unstable. And so they start positron emitting or electron capturing or alpha emitting or beta emitting and so on. And so they have extremely short half-lives, which means they're incredibly radioactive. So as soon as we pull the spent fuel out of the reactor, it's so hot you can't even go near it. It's all done robotically. So we set those really super hot fuel in this cooling pool. So this has got a water level here that's keeping these canisters cool. And that's what this generator is for. This generator runs the pumps that keeps this water level circulating. Well, in this earthquake, we got a crack in the building right here in the spent fuel area. And that water started leaking out. And the generator could have kept it up by pumping water in there, but the tsunami that came in was a little over 5 meters tall. And so it was just enough to ground out this generator and destroy it. So the generators weren't working, and they had no way to get in there and like put in a new generator in time. And so what was happening is this water level was leaking out. They were trying to spray it in with trucks, but that water level dropped, and the spent fuel became exposed to air. Well, we looked at thermal conductivity. Thermal conductivity of water is about 1,000 times more than air. So the exposed metal on these fuel canisters to air was getting super, super hot, because air is not taking away the heat as fast as the water is taking away the heat. And so right at that edge where you have a super hot metal and water, you can thermalize. It is hot enough to take water and run that reaction backwards to make hydrogen and oxygen. So we were getting the reverse reaction of hydrogen and oxygen making water because it was really hot at that fuel spot. And so it was not the nuclear reactor that created an explosion, it was the spent fuel that created an explosion. So we thermalized water, so we had the stoichiometric amount of hydrogen and oxygen in this little metal headspace, which all you're just waiting now is for something to set that off. Yeah. And you can find the explosion on YouTube. It blows this square roof straight up, like it's a perfectly symmetric gas explosion. And they knew it was going to happen anytime, so they didn't have anybody by. And sure enough, they have this security footage, and this goes. You see this poof, and the roof just goes right out of frame, like straight up. And so that was a mess. Now there was one reactor in this. They call it a suppression pond wet well. There was a crack in one of these cooling areas. This is the primary cooling loop, and so some radioactive water leaked out, and so now it's moving through the environment in Japan, and so they're able to detect where it is. And so what they've done is they've drilled wells down there into the groundwater, and they're pumping that contaminated radioactive water out, and they're treating it. and then discharging it. So it's called a pump and treat remediation. And so since you can detect really low levels of radiation, they're pumping up the radioactive water, they're sequestering it on filters, and then the non-radioactive water is going back into the groundwater to prevent this plume from spreading. So this is a known way to treat environmental contamination, not just nuclear, but we do it for petroleum contamination. If you've got a gasoline, storage facility and it leaks an enormous amount of fuel into the environment, we can pump out the contaminated water, treat it, and keep that plume from spreading. So the thing that made me angry about this whole thing was the media overplaying the danger to the workers and so on. I mean, no doubt we had a nuclear meltdown. The fuel didn't get cooled, it melted. We had a release to the environment. You may have heard of 3 Mile Island. That was a nuclear, there was the cooling water sprung a leak, and it was contained within the building. So it didn't even have an environmental release. Nobody got irradiated, nobody got killed or anything like that. But this was way worse than 3 Mile Island. It had an environmental release. We have radioactive water coming out of the Fukushima reactor. But the media was talking about the brave control room people who are going to die. They're working in their graves. They've all received a lethal dose of radiation. You can look at the news reports from this, and it was totally malpractice, in my opinion, because it says one female worker received 1.7 rem. It was above the limit for female workers of half a rem each 3 months. Okay, it was no impact on her health. And there were 201 people working there. They had 645 people at the whole plant, and no workers went above the 25 rem threshold. So they didn't see any detectable clinical effects. 30 went over 10 rem. Okay. And yet, after the media hype over this thing, you had countries making decisions, drastic decisions, like Germany deciding to phase out all of its nuclear power activities. It's crazy. Like, there's such an overreaction driven by the media. So there's just another reason why I hate the media, because they don't do their research, they don't know what they're talking about, and then they hype things up. And you have, dramatically bad decisions being made by countries based on that. So let's look at implementing nuclear power. There's a comparison. You can look at the construction, operation, and maintenance of different power plants and so on, and look at the amount of deaths there are per 1,000 terawatt hours, or 3.6 exajoules of electricity generation. And coal, by far, from the mining, the transport, and the production, maintenance, and operation of coal-fired power plants, has the worst safety record of 100,000 deaths per 1,000 terawatt hours. Oil is better, natural gas is even better, hydroelectric is better, rooftop solar, wind, and nuclear are the best. And so for 425 exajoules per year, we could do the math. For nuclear, that would be 10,600 deaths per year, and for coal, that would be 11.8 million deaths per year. So this is if we did everything on coal. If we did everything on natural gas, it'd be 472,000 deaths per year. Wind, 17,000, and so on. So again, the nuclear power industry has got an incredible safety record. Now, some of the rubble, like I said, that rooftop of the reactor, when it blew off, if it went up, it's got to come down. And so that was a highly radioactive piece of metal. You had sheet metal and some, structural steel and so on. When it blew up, it came back down, and it was pretty high. So how do you clean that up? Well, you use robotics. And so here's a robotic forklift and trash truck, it goes in and grapples and picks up the highly radioactive material, puts it in the truck, and then takes it to a place where it can be safely disposed. We do have here in the United States, the Nevada Proving Ground and the Nevada Test Site, we do have some long-term storage of highly radioactive material. We have several, I don't know how big it is, but probably probably like a football field of sand from a beach in Spain, where we were doing a refueling, aerial refueling of a B-52 bomber that had nuclear weapons on board back in the 60s. And the tanker and the plane crashed and both went down. And when the nuclear weapons hit the beach in Spain, they went off. The explosive went off, but the nuclear part didn't go off. But it still sprayed radioactive material all over the beach. So what we do? We went and cleaned up the sand, put it in drums, and it's sitting in Nevada. Why? Well, because plutonium has a half-life of 24,000 years. And so it's going to be radioactive for a long time. Yeah. Now, they probably could have extracted it. They probably could have, the chemistry of sand is going to be different than plutonium. So they probably could have extracted the plutonium and put it in a smaller container. But still, we have a lot of sand, radioactive sand. So this rubble was picked up, and it gave 330 rem per hour. So in 1 hour, let's say you didn't know what you were doing, you go over, you start picking up that scrap metal and throwing it into the dumpster. In 1 hour, you would have a detectable clinical effect. You would start to show radiation sickness. And that's what we saw with Chernobyl. So the Chernobyl explosion, if you haven't seen the HBO special about Chernobyl, it's really good. And they were telling people to just clean up the reactor core. The graphite core had just blown out of the roof. And so they were picking up chunks of highly radioactive bits of core, and these guys were dying days later. Yeah. So let's talk about radiation sickness and radiation exposure. So there's two theories. The threshold theory, which is what I've been talking about. There's a threshold below which the body can handle radiation doses. So 25 millirem, 25 rem, seems to be the threshold before we can even detect a physiological response by our body. Also, the threshold theory is doses aren't additive, and we'll talk about what that means in a second. And then there is this sort of side theory that talks about hormesis. So if you have weak cells that are susceptible to damage, radiation can help cull out those weak cells. Now, that's a bit controversial, but the threshold part is not controversial. Let's look at this one, though. This one is crazy. This is the linear no threshold theory, the LNT theory, still present today, okay? This says all doses are detrimental, no matter how small, okay? That's a nice sort of way to operate. Like if I'm going to work with radioactivity, I don't ever, with that smoke detector, put my hand directly in front of the beam. Why? Why increase my dose? All right. So I'm kind of behaving as if the linear no threshold theory is true, but it's physiologically not true. But it's a good sort of practice. Keep it as low as reasonably achievable. But this is the thing that I disagree with 100%, that doses are additive. Okay. It played a political role. This linear no threshold theory played a political role in 1959 to enact the atmospheric test ban. We were in an arms race with Russia, and they were doing atmospheric testing, and we were doing atmospheric testing. We had sort of satisfied our goals with our weapons program to a large degree, and we're considering doing underground testing. We had a Nevada test site, and we wanted the Russians to stop their development. They were doing atmospheric tests. And so we started this scare tactic of saying, oh, radiation is special. No matter how small the dose, it's damaging. And it accumulates over your lifetime, so that, if we keep doing atmospheric tests, then we're killing everybody on the planet. And so that's where this hysteria over radiation really started. We started beating that drum in the media again. And so it was a scare tactic, and it was effective. But the scare tactic has continued to this day. People hear about radioactivity and they recoil in horror. But let's think about if we applied this linear no threshold theory to any other kind of thing. Okay, you've breathed in automobile exhaust, right? You've walked across the street. The linear no threshold theory would say that every one of those little exposures is detrimental and that they're additive. So one of these days you're going to walk across the street and pass out from CO poisoning, carbon monoxide poisoning. And that's not the case, because your body's already dealt with the insult that it received yesterday or 10 days ago or a year ago. Same with water. If you ever swallowed wrong and got water in your lungs, you cough, it's irritating, and so on. The linear no threshold theory would be someday you're going to swallow wrong and you're going to pass out because you drowned. But no, that's not the case. You've already processed the water that was in your lung if you swallowed wrong yesterday. And so our bodies just naturally clear out these environmental insults. And that's sort of toxicology 101. We have absorption, distribution in the body if it's a toxin. We metabolize those toxins and then we eliminate them, either through our GI tract, urine, we sweat it out, we breathe it out. So there's four or five different ways to eliminate things. So ingestion exposure time is governed by metabolism and elimination rate of toxins. So we talked about the biological half-life of the chemical species, but external radiation we govern by time, distance, and shielding. And y'all did that in lab. You measure the dose, it's linear with time. You measure the shielding, it's linear with shielding, the thickness of the shielding, depending on paper or tin or aluminum. But then the distance is you'll see when you analyze the data, is an exponential decay. So you get twice as far away, your dose drops dramatically. And then it also is governed by this metabolism rate of damaged tissue. And then elimination. So this is your normal toxicological treatment. We've already talked about the 50% or LD50. Then there's this lowest observed as adverse effect level. So that's that 25 REM. And then there's this no observed adverse effect level. Like below this, you don't even observe anything. Okay. And so then there's down here, normal biological variation is in play here, but up there, LD50, and then the sort of the 90th or 95 percentile is the Frank effect level. So you've gotten, if you get above that, you know you're dead. So these are the biological half-lives of toxic substances. You got nickel, mercury, arsenic, cobalt, mercury. The mercury is here twice. You see the diamonds are blood and the circles are urine. So we can detect mercury in the urine. This is the half-life. So here's 1 week and it's 1 year. So this is sort of a logarithmic scale. So on the order of months, we can detect an acute mercury exposure for months in the urine. We can detect it in the blood for weeks. Look at this. Cadmium is the worst one. Okay, its biological half-life is over 10 years. So cadmium is going to be in your body a long time. So if we had a radioactive element that was similar chemically to cadmium, it would be in our body for a very long time. And so that's where you're reacting to the ingested radiation. But as far as the radioactive insult, let's say it's external, it's treated as an injury, not a toxin, like a sunburn. So a sunburn isn't a toxin, a sunburn is an injury. And this is the same mechanism. Radiation comes in and it can damage your tissues and it can sort of burn your tissues. Now, some toxins can create hypersensitivity, like tree nuts, latex, you've heard of this. And you can have long-term, no-effect doses of substances that accumulate that may cause hypersensitivity or health effects, like cadmium, lead, mercury. And then there's some people that they have an immune system that doesn't recognize cancer cells. Most of us, at least I could probably say all of us in this room, because y'all are you're not quite 20, are you? 21, 22, that range. You guys would have already had cancer if you didn't have the ability to detect cancer cells. Because all of us have probably had cancer cells and our bodies have detected them and killed them before they had a chance to get out of control. So people that aren't able to kill damaged or cancer cells get cancer early in life with normal environmental exposure. So there's really no physical way for us to accumulate radiation. We get damaged by radiation and then metabolize the damaged cells. Radon gas we've talked about. It's chemically inert and highly mobile, percolates through the ground. Then once it gets into the lungs, if you're unlucky, and that's the time when this radon decides to decay, then now you've got polonium in your lung. Okay, you look at radon, alpha particle, we get polonium, alpha particle, you get lead, and so on. So It's a crazy bad luck, though. Think about it. Radon has a half-life of about 4 days, and yet it's taken years for it to percolate from the nucleus it came from down in the soil, percolate through. How many half-lives has it gone through? And yet that nucleus of radon is still not decayed, because there's a huge distribution statistically. You've got some radon that decays really fast, some radon that goes hundreds of years, thousands of years before it decays, and it gets in, you breathe it in, and it's just crappy luck. Now it decays, it decides it's my time, and it splits out off a particle, and now you've got it in your lungs. Now that we've used these radioactive isotopes to do some really fantastic things. We talked about thyroid. So iodine 131 is good for imaging the thyroid. So it looks like it's looking at his shoulder, but it's sort of supposed to be the thyroid in his neck here. If the iodine is absorbed by the thyroid, then the thyroid's going to glow like crazy. And so we have these collimators. Look at how many photons are lost by the collimators, right? So they're at the wrong angle. And so these collimators just take like image straight up so that you can detect. You hit the phosphor screen, it scintillates, means it turns it into visible light, and then you detect that with your detectors. So this would be the old style scan with collimators, phosphors, and visible light. Okay. We can use other radioactive isotopes to detect other things, but this is the old school way. Now let's look at the positron emission tomography. So notice we don't really lose anything to the collimators, and the annihilation. So this positron comes together with an electron, -1, 0, and gives 2 gamma rays. Now, the one thing that I love about physics is that the conservation of momentum is preserved, whether you're at the atomic scale or at billiard ball scale. So 2 particles of mass come together and hit. One is matter, the other is antimatter, but they still have mass. They hit each other and they annihilate and turn into energy, but you still have momentum. And so the momentum of the particles is turned into light, which still has momentum. So these particles, the light comes out in opposite directions. So the particles, if they're going to collide, have to be going towards each other. So they go towards each other, turn into energy, and then the light comes out. And it's a simultaneous event. So this light comes out, at the same time. And so we can tell our computer if any of these detectors gets like a cosmic ray comes in and hits this detector, and it sends a signal to the computer. The computer says, okay, I'm going to look at the opposite side. Did I get any other photons at that moment? And if the answer is no, throw away that signal. So it has a 0 background. So unless you get simultaneous detectors hitting, then it wasn't a positron emission. So this has revolutionized the imaging, because 0 background is what you want. You've got cosmic rays, you've got radioactive elements in the concrete. Even in our lab, 13 counts per minute is hitting those detectors, and they're going off. But the computer's like, nope, it's a non-simultaneous event, so we don't care about it. So it's able to sort of get rid of all of the noise, and you end up with a very clean spectrum. So this is a comparison. This is not in your notes. I put this in this morning. These are different medical imaging techniques. So straight up x-rays, you see the bone structure. You see the teeth, the jaw, the cranium, the backbone, and so on. But you don't see any soft tissue. You really don't see much about the brain or anything like that. But you can, using straight x-rays, you can get the bone structure. A CT scan is an x-ray technique, but it's called computed tomography. So it takes sort of slices of the x-rays and uses a computer imaging to stitch those pixels together. And so you can get a 3D shape using computed topography and tomography, and then it can clean the image up and give you a higher resolution. And then you can kind of see some of the soft structures. Here's the brain. You can see the tongue. You can see the palate. So you can see some softer tissues in CT. MRI is even better. So magnetic resonance imaging. They can focus in on the proton signals, and they can get a higher resolution. They can put in a contrast agent, so they can, like if they wanted to image the blood flow, this is a magnetic resonance angiogram. So that's the blood flow. You see all of the blood flow around the spine and the brainstem, and then going up into the brain. You can see all of those. Very good technique for looking for strokes, brain bleeds, and things like that. And then the PET scan here in color, you can see just a higher resolution of the brain structure. You see differentiation too of what's going on in the brain. The nice thing about the PET scan is it does give you chemical information. So there's, I was talking about carbon 10 or carbon 11, I think, as a good source of PET scan. Positron emitting carbon, but looking this morning is fluorine 18. So they can take a sugar molecule, pull off an OH group, and put a fluorine 18 in there, and sort of tag that, and it will go where sugar goes. So they can make glucose with the fluorine 18 tag, and that's a positron emitter. The idea is to, if you're trying to image cancer, to try to put something in there that the cancer really wants, like sugar. Here's an example also. We got MRI, CT, and then this is saying that now they're making combo machine. So they're making machines that do MRI and positron emission tomography, because you get different resolution, and the same with CT PET. So here's an MRI, here's a CT, and here's the PET scan. Notice you can see say this is a tumor, you can see the structure there. You can see it in the MRI. Let's look at the lung, actually. You can see this mass here in the lung. I mean, I'm not a doctor, but I can say that's not right. Okay. I can see it in the CT, but it's not as well defined. But look at the boundary. You can really get a feel for the boundary, the full extent of that mass in the PET scan. Okay. And again, I don't know what organs are down here, but yeah. I don't know if that's the pancreas or the stomach or what. Now, what's that? It is right here? It looks huge. Yeah. Maybe it's this tumor on the kidney. Yeah. Then down here you see the bladder, right? And of course you're eliminating a lot of this stuff too. So the bladder's glowing like crazy because it's filled up with the stuff. So now the nuclear fuel that we have, we're out of time. Sweet. Well, we'll talk about nuclear energy next time. Here's a medical isotope reactor up in Dayton, Ohio. And you can put your stuff up while I'm talking about this. You can see the reactor down here. So that's the fuel assembly here. And they have these little tubes that go down. And you've been to the bank, right? You put your deposit or whatever in the little tube and blow it over. That's how these work too. So they'll blow it down in there, expose the heck out of a target to make a radioisotope that's medically useful, and then they'll suck it out, go extract it, and these are the chambers that they use to do the extraction. These hot cells.